Hello friends, today we are going to discuss about the application of moment of inertia. The first application is moment of inertia of rectangular body. This is a rectangular metallic plate PQRS. There are two different axes like x-axis and y-axis. Both are mutually perpendicular but both are in the same plane of that plate, and there is a z-axis perpendicular to the plane of that plate, also perpendicular to the these two axes. So we have to find the moment of inertia of this rectangular body. We are considering here a very small part. This is a small element dx whose width is dx, and the distance of this small element from the axis y dash is x. So for finding the moment of inertia of this body about y dash, initially we have to find the moment of inertia of this small element, and by taking the integration, we'll get the moment of inertia of body about this axis y dash. Similarly, we'll get the moment of inertia about this x-axis and z-axis. So how to find this moment of inertia? We'll see in detail. So this is a rectangular metal plate whose thickness is uniform. The length of this plate is L, breadth is B, and suppose the axis passing through the center along y dash in the plane of that plate. When we consider a small element dx, the width of that element dx element is dx, and the distance of that element from the axis y dash is x. As we know, the mass of that plate is suppose capitally M. Area of this plate is length into breadth, that is L into B. Mass per unit area, that is mass upon area, M divided by L into B. Then area of the small element, we have to find area of small element. So area of small element is B into dx, where B is the length of that small element, dx is the breadth. Then mass of the small element is M upon LB into B dx. So BB get cancelled. So remaining part is the mass of that element M upon L into dx. Now moment of inertia of the small element about the axis y dash. So when we find the moment of inertia of the small element, mass of the small element into square of the distance from the axis of rotation. So mass of the small element is m upon L into dx, and the distance square is x square, from which we'll get the moment of inertia of whole plate about this axis y dash. So it is denoted by Iy is equal to m upon L integration whose limit from minus L by 2 to plus L by 2 x square dx. Now m upon L, this integration is x cube divided by 3, and whose limits are L by 2 and minus L by 2. Upper limit is L by 2, lower limit is minus L by 2. Now put the values of limits in this variable. So Iy is equal to m upon L, that is equal to L cube upon 8 divided by 3, that is L cube divided by 24, and minus of that minus we get the plus L cube divided by 24. Now 2 times of L cube divided by 24, that is L cube divided by 12. So in this way we can write this equation as Iy is equal to ml square upon 12. Similarly, the moment of inertia of whole plate about the axis x dash, this can be written as a Ix is equal to mb square divided by 12. So instead of that length, we are taking here breadth, and for finding the moment of inertia about that x-axis, this is the x-axis. So we should consider the breadth of that particular part. So we are getting the value of mb square divided by 12. Now moment of inertia of the plate about z-axis, that z-axis passing through the center but perpendicular to the plane of that plate, and by using perpendicular axis theorem we can find this value. Iz is equal to Ix plus Iy. So Iz is equal to, the value of Ix is mb squared divided by 12. Iy is ml squared divided by 12. So take common m upon 12 from these two terms. So m upon 12 inside this bracket L square plus b square. So this is the moment of inertia of rectangular plate about the z axis, which is perpendicular to the plane of plate and passing through the center. Now the moment of inertia of same plate but axis passing through one side like PS. So how we find this particular value? By using parallel axis theorem. So this value is IPS is equal to Iy there is moment of inertia about moment of inertia of the body about the axis passing through the center plus the mass into distance square. So IPS is equal to this value Iy is ml square by 12 and plus this m into L square divided by 4. Now multiplying 3 here, numerator and denominator. 3 ml square divided by 12. So 3 plus 1, 4. 4 ml square divided by 12. That is 4 by 12 is 1 by 3. So ml square by 3 is the moment of inertia for the particular plate when axis passing through the breadth line. Similarly, we can find the moment of inertia of the same plate about the axis PQ. See, this is the PQ. So, when the axis passing through this line, we get the moment of inertia. That value is IPS is equal to, in the same way, Iy is equal IPQ is equal to Ix plus MB by 2 this bracket square. Now Ix is MB squared divided by 12 and this is MB squared divided by 4. So 3 MB squared divided by 12, 3 plus 1, 4, 4 MB squared divided by 12, that is 1 by 3 times of MB squared. So this is the moment of inertia of the metallic plate when it passes, the axis passing through the PQ. Similar to that, we find the moment of inertia about moment of inertia of cylindrical body. So how to find the moment of inertia of solid cylinder about the axis passing through the center but perpendicular to its length. So this is a solid cylindrical body. This is the axis of the solid cylinder x dash, and this is the axis passing through the center but perpendicular to the length. And we have to find moment of inertia of the solid cylinder about this axis, that is y dash. So length of this cylinder is L. R is the radius of cross sectional area. M be the total mass of the cylinder. Then mass per unit length is M by L. Now y dash is the axis passing through the body for which we have to find the moment of inertia. For that, we have to take a small element. So this is a small disk of width dx. We should consider this is a small disk d whose width is dx and the distance of the disk from the axis of rotation is x. Okay. As we know, the moment of inertia of any disk about its diameter. Suppose the axis passing through the diameter. Then what is the moment of inertia about the disk for the axis passing through its diameter? That is m r square by 4. So for this disk, how to find? So mass of this disk is m by L into dx, whose radius is r. So r square divided by 4. So moment of inertia of the small disk about its diameter is this value m by L dx r square upon 4. Now moment of inertia of the same disk but axis is now passing here y dash and we have to find only for the moment of inertia of this disk. So moment of inertia of this disk about the axis of rotation y dash is m by L dx r square divided by 4 plus mass into that, mass into distance square. So m by L into dx into the distance is x square. Now, the moment of inertia of cylinder about y dash means this is the moment of inertia of entire cylinder. So, moment of inertia of entire cylinder about the axis y dash is I is equal to 2 times of y, 2 times of because there are two parts. From this is the half part and this is also half part. So, we have to take from 0 to L by 2. When we consider the limit 0 to L by 2, we have to take another part of that left hand side. So 2 times of integration from 0 to L by 2, this quantity is m by L dx into r square divided by 4 plus m by L dx into m by L into dx into x square. Now take common m by L. So 2m by L integration whose limit from 0 to L by 2, here r square by 4 plus x square into dx. Now I is equal to twice m upon L by taking the integration r square by 4 as it is here, but instead of that we can write here for x plus for x square whose integration is x cubed by 3 and whose limits are 0 to L by 2. Now put the values of limits. Twice m by L, here r square by 4, and x is a L by 2. This is the upper limit, plus, and lower limit is 0, so not necessary to use this. Plus here L cube upon 8, further divided by 3, so L cube divided by 24. Now I is equal to m, take 2 common from these two terms. So 2 get cancelled. So m by L r square upon 4 into L plus L cube divided by 30. Then I is equal to, take L inside it, so L get cancelled, and here one L cancel. So m in bracket r square by 4 plus L square by 12. So this is the moment of inertia of solid cylinder about the axis passing through the center perpendicular to its limb. Then how will you find the moment of inertia of solid cylinder about its axis? And about this axis, the moment of inertia for that axis is I is equal to mr square by 2, which is a direct value. Direct value means these values are actually proved in the previous standard. Now moment of inertia of solid sphere. So moment of inertia of solid sphere about an axis along its diameter. So solid sphere whose radius is r, the capital M is the mass of the sphere, volume of the sphere is 4/3 pi r cube, mass per unit volume is m divided by 4 by 3 pi r cube. Now we have to take an element of thickness. This is a small element of thickness dx, and the distance of this element from the center is x. So radius of this element, what is the radius of this element? The radius of this element is r square minus x square, and taking the square root will get this value. So radius of this element r is equal to capital under root capital R square minus x square. Now find the volume of this element. How to find the volume? Area of this particular area of cross section into width of the thickness. So volume of this element is pi r square into dx. Now pi r square, instead of that r square we can write here capital R square minus x square into dx. Mass of that small element m divided by 4 by 3 pi r cube into pi r square minus x square dx. Now mass of this element is thrice m divided by 4 pi get cancelled, so 4 r cube inside the bracket r square minus x square into dx. Now moment of inertia of the small element about axis, about this axis passing through its center. So that value is 1 by 2 mass into square of the radius. So moment of inertia of the small element I is equal to 1 by 2 thrice m upon 4 r cube inside the bracket r square minus x square dx into the square of radius r square. Now this value becomes 3m upon 4 r square r cube in here inside the bracket r square minus x square, and r square divided by 2 into dx. Now this 3m upon 8 r cube, and this value is r square minus x square, and instead of that r square we can write here r square minus x square dx. Now I is equal to thrice m upon 8 r cube, here r square minus x square raised to 2 dx. So moment of inertia of whole sphere I is given by I is equal to 2 times of this value from integration from 0 to r thrice m upon 8 r cube inside the bracket r square minus x square bracket raised to 2 into dx. So take common thrice m upon 4 r cube and integration from 0 to r, r raised to 4 plus x raised to 4 minus twice r raised to 2x square dx. So this is I is equal to thrice m divided by 4 r cube inside the bracket, here r raised to 4 into x plus x raised to 5 divided by 5 minus 2r square into x cube divided by 3, and whose limits are 0 and r. Upper limit is r, lower limit is 0. According these limits, I is equal to thrice m upon 4 r cube, here r raised to 5 plus here r raised to 5 divided by 5 minus twice r raised to 5 upon 3. So take common this, and after solving I is equal to thrice m r square divided by 4 into 8 divided by 50. So finally it becomes 2 by 5 times of m r square. So similarly, we can find the moment of inertia of solid sphere about an axis tangent to that sphere by using the parallel axis theorem. So it is equal to id plus mr square. So id value is 2 by 5 mr square plus this value mr square. So from which we can get this value, it is equal to 7 by